We want to discuss a reversible process because, as we'll see, a reversible process by itself does not lose any energy to the environment. We will then construct a heat engine using only reversible processes, and that will allow it to be the most efficient engine that's possible. This perfect engine is called a Carnot engine, and we will use it to determine the maximum efficiency permitted for any heat engine. So that's the plan, and we'll get back to the Carnot engine, but first let's discuss what is meant by a reversible process. It's so called because after it follows a path from one state to another, like this, it can then follow the same path back, like this, so that over a complete cycle, the energy into the system equals the energy out of the system, and no energy is wasted. Such a process can only be accomplished if the system changes so slowly that each macro state is defined at every step along the path. If the process deviates from this reversible path, then additional energy must be added to the system from the environment to complete the cycle, and the cycle is not as efficient. It is actually not possible to have a perfectly reversible process because any change in the system, such as the addition of heat or a change in pressure, will take some finite time to be evenly distributed throughout the system. And because the system is continuously changing, think of the movement of the piston as an example, then the system never gets the chance to be completely in thermodynamic equilibrium. This can be approximated, however, by transitioning very slowly, which is called a quasi-equilibrium process. Even though a real process is not completely reversible, we can use the concept of a reversible process to build a perfect heat engine and determine the fundamental limit of the efficiency of any heat engine. So to summarize, there are two idealized conditions that make a process reversible. No energy is lost to the environment as a result of friction, air resistance, etc. And as the system transitions from one state to another, it is continuously in a state of thermodynamic equilibrium, that is to say the macrostate variables are uniform throughout the system. These conditions ensure that a reversible process does not require additional energy from the environment and make a reversible process by itself 100% efficient. But remember, we need to take a different path back to produce a net work in a complete cycle, so we can't just use a single reversible process. We will actually need to combine two types of reversible processes to accomplish our goal. So let me describe such a process that uses only reversible processes and produces work. A piston starts in position A, where the gas is already compressed and hot. A temperature reservoir at this same temperature is then placed in contact with the piston. The temperature reservoir is large enough with enough heat capacity that it will remain at this temperature, TH in the figure, even if it loses some heat. Because of its contact with the piston, it will transfer heat as necessary to keep the piston or the gas in the piston at the same hot temperature, even as the piston moves. So now, because the gas in the piston is compressed, it forces the piston to move up like this. As the piston rises, it pushes up and does positive work on the environment, whatever is external to the piston. The work is positive because the gas volume increases. As the gas volume increases, its temperature would decrease according to the ideal gas law, but heat is added to the gas from the hot temperature reservoir, something like this. As it moves up, the piston eventually reaches, say, position B. At this point, the hot temperature reservoir is removed. The gas pressure is still high, so the piston continues to push up and continues to do positive work. Without the temperature reservoir present, the piston is now thermally isolated, so no heat can be transferred into or out of the gas. As the gas expands, therefore, it begins to cool according to the ideal gas law. The piston then reaches a maximum height at position C. At this point, the gas is cooled from its original hot temperature, and a cold temperature reservoir at this cooler temperature is placed in contact with the piston to keep the gas at this cooler temperature, which I've labeled as Tc in the figure. The piston is then forced down by another force on the piston which isn't shown, and during this phase the piston does negative work because the gas volume is decreasing. The temperature would increase, again according to the ideal gas law, but heat is removed by contact with the cold temperature reservoir, and so we can show heat going in this direction. The piston continues and eventually reaches position D, say here. At this point, the cold temperature reservoir is removed. Now the external force continues to compress the piston, and the gas continues to do negative work. As it is compressed, the piston is thermally isolated again, so no heat can be transferred into or out of it, and the gas temperature begins to increase according to the ideal gas law. The piston then reaches the original position A. At this point, the hot temperature reservoir is reapplied, and we're back to where we started, and the cycle repeats. Here are the key states of the cycle we just described. So between A and B, we said that heat had to come out of the hot reservoir and into the piston, and I'll just show that here in the middle. And conversely, between C and D, we had heat leaving the piston or leaving the gas, and I'll show that here. Between B and C, say like this, that's when it was isolated, so there was no heat transfer, and the same between D and A, no heat transfer. And then we had positive and negative work occurring all along the way. So between A and B, we had positive work. Also between B and C, we had positive work. But then as it was compressed, so between C and D, we had negative work, and between D and back to A, we had negative work. Each individual transition from A to B, B to C, C to D, and then D to A is theoretically a reversible process if we use infinitesimal steps and allow the system to reach equilibrium each time. As I said, this isn't practical, but it is efficient. In fact, it is the most efficient cyclical process possible for a heat engine, which is what we're going for. So let's plot this entire process on a PV diagram. Now notice the shape of the curves I use for the paths between the states. These curves are paths associated with reversible processes. There are actually two different types of reversible paths here. The transition from A to B and from C to D, where the temperature was held constant, is called an isothermal process. The transitions from B to C and D back to A, where the system was thermally isolated and there was no heat transfer, are called adiabatic processes. Let's take a closer look at each of these processes to see what the curves look like mathematically and why I drew them this way. We'll start with the isothermal process. As we said, an isothermal process is when the temperature is held constant. Given that, we can use the ideal gas law to find the basic shape of the curve. So here's the ideal gas law. Since the temperature is constant, this whole quantity is a constant. Let's just label that C, and then I'll solve this for pressure. So that would be our constant C times 1 over the volume. Now mathematically, this whole equation is a hyperbola. And so I'll add that to the description for the isothermal process. And so the curve from A to B on the PV diagram would look something like this. Similarly, C to D is an isothermal process, so the curve is hyperbolic and will look something like this. Now let's take a closer look at the adiabatic curves. As we said, an adiabatic process is isolated, so there's no heat transfer. Let's again start with the ideal gas equation to analyze the basic shape of this curve. But this time temperature is not constant, and K of course is, and I'll use a C again for that. So let's solve that for P, for the pressure. So that would be our constant C, 1 over V, and then times the temperature. So we can see because of the changing temperature here, it's not exactly a hyperbolic curve this time, but we can analyze what happens to the temperature and then make a qualitative determination for what the PV curve looks like. So let me draw a line here, and then to analyze what happens to the temperature, let's use the first law of thermodynamics. Now in the adiabatic process where it's isolated, that makes Q 0. And we can also replace the internal energy with the equation that we came up with before. And so substituting that in, and so all of this is a constant, which I'll move to the other side and solve this for delta T. And I'll call that constant, I'm inverting it, but I'll just call that C prime. Put the negative out front. So that's really just the negative constant times the work. So for an increasing volume, this is positive work for increasing volume. And so mathematically, since this is the negative of that, this delta T must be decreasing. So just based on this analysis, let me squeeze it in and put it over here. We can just say that T decreases as the volume increases. So what does that mean up here in our original equation? So this decreases as the volume increases. So what that does is it takes this hyperbola and it basically rotates it clockwise just a bit. Or I'll say it this way, that this is a steep hyperbola. That's not an official mathematical term, but that'll be good enough for our discussion. So let me just make a note of that up here, that this is basically a hyperbola, but it's steeper. And so this steep hyperbola connecting B to C would look something like this. The exact equation for an adiabatic curve can be derived, but this qualitative description is enough for our analysis. And the process from D to A is also adiabatic, so the curve from D to A would also be this steep hyperbola and look something like this. So connecting the dots between A, B, C, and D, we get the complete cycle I described with the piston, and only using reversible processes. And we can clean up the picture a bit and just show the paths between the states. And it's also a common practice to show where heat is transferred and where work is done in the diagram. Let me start with the work. So as we said, work is the area enclosed by the curve here. So all of that is the work by the engine. And then showing the heat transfer. So that occurs during the isothermal curves. And so that's here. Here's one of those, which means a constant temperature. Constant, let's say that's the hot temperature. Or down here, that's the other isothermal curve. And this is a constant cold temperature. While we're labeling the curves, here's the adiabatic one, where Q equals 0, and then here as well. And so showing the heat transfer, here we have heat transferred in from the hot reservoir, and then down here heat transferred out to the cold reservoir. So this complete cycle is the Carnot cycle, which is named after the French physicist who first theorized it to investigate how efficient a heat engine can be, as we're doing right now. There's one more condition of a reversible process that will be important and useful as we investigate the efficiency of the Carnot cycle. This condition is that a process can only be reversible if it does not increase the disorder of the universe. That may sound more like philosophy than science, but there is a statistical foundation for it. To understand it, let me first ask, why will an ice cube absorb heat and melt, but it won't spontaneously, that is to say on its own without external influences, re-emit that heat and turn back into an ice cube? Or why, when a glass shatters, will it not spontaneously reform back into a glass? Or why does heat only spontaneously flow from a hot object to a cold object and not in the other direction? Which, by the way, is a fact we have been relying on as we have discussed heat engines up to this point. None of these processes is reversible, but why? What law of nature tells us that these processes cannot spontaneously occur in reverse? Doing so can still conserve energy, so they do not necessarily violate the first law of thermodynamics. The answer is that there is another law of nature, and that law is the second law of thermodynamics. But before I give you the compact language for that law, let me give you a conceptual explanation for it. Statistically, any system will only spontaneously evolve into a more probable macrostate and not into a less probable macrostate, which sounds like a reasonable statement to make, I think. And by the way, just to be clear, you keep hearing me say spontaneously a lot. It basically means that the system is left to itself and is isolated from outside influences. Anyway, this idea explains why the examples I just mentioned, such as an ice cube melting and heat flowing only from hot to cold, can only happen in one direction. These systems are evolving into more probable macro states, and they won't return spontaneously to less probable macro states. Now here's the statistical part. The probability that a system will be in a given macro state is determined by the number of ways the particles in that system can be arranged to form that macro state. So a system is more likely to be in a macro state that has more ways to form it. So to make that point, let's consider tossing some coins. Let's say you have 3 coins and toss them on the table. Are you more likely to get all heads, 2 heads and a tail, 2 tails and a head, or all tails? The answer is based on the number of ways you can get each combination. Here are the different ways the 3 coins might land. In the first row, all are heads. In the second row, 2 coins are heads and 1 is tails, and so on. Notice there is only one way to get all heads, but there are 3 ways to get 2 heads and 1 tail. And there are also 3 ways to get 1 head and 2 tails. And then finally, just 1 way to get all tails. Because there is only one way to get all heads, or all tails, these are the least likely outcomes. But because there are 3 ways to get 2 heads and a tail, or 1 head and 2 tails, these 2 outcomes are the most likely. So this is a simple example, but it has very large repercussions in nature. As an example in thermodynamics, consider an empty container, meaning it's just a vacuum inside, into which a volume of gas is released in one corner like this. The gas will quickly spread throughout the container. Let's say the initial state is A and the final state is B. In state A, the gas molecules are in a smaller region, so there are fewer positions the molecules can be in to arrange themselves to form that state. But in state B, there are many more positions the molecules can be arranged in to form that state. Because there are so many ways to arrange the molecules in state B is more likely to occur. Or said another way, once the molecules spread out into the more probable state B, they are not likely to return to state A. And in fact, it's much more dramatic than that. The number of permutations involved in this analysis is enormous. So in the end, the chance of state A reoccurring is essentially 0, and we never see it happen. You've probably heard the term entropy before. Entropy is the macro state property that represents the number of ways a macro state can be formed, and therefore how likely it is to occur. I'll give you a mathematical definition of entropy in a minute, but just given this conceptual definition, let's now state the second law of thermodynamics.